We're going to start today by just Derek here in the front would like to turn around and say hi to his mom.
Hi, Mom. Okay, bye.
So you wanted to be on YouTube, and also you wanted to be in the front today. Yeah. All right, what's the plan for today? The plan for today, class number 6. Lecture A is to talk more about normal curves on spreadsheets and a lot more on correlation and regression. And then lecture B will be more in chapter 3 for our textbook, populations and samples, observational studies versus experiments, sampling in general, and bias. All right, what about normal curves? Actually, let's look at this particular slide a little bit more closely. I think this is a good slide to look at periodically. Maybe we'll get that way too. Why don't you zoom in on it? It's a pretty nice picture, giving you lots of different areas. For example, the area between a z-score of -2 and a z-score of -1.5 is about 4.4%, meaning for data that are normally distributed, that have a histogram that looks somewhat like this, you can expect about 4.4% of the data, maybe you'd round it to 4%, would have a z-score between -2 and -1.5. So that's one nice thing about it. Another nice thing is you've got this cumulative percent scale down here. That can help you find percentiles based on z-scores and vice versa. So for example, a z-score of 1 standard deviation above the mean, is essentially at the 84th percentile. The 60th percentile, on the flip side here, essentially corresponds to a z-score right around 0.25 or perhaps 0.3. So that's kind of nice too. But we can also find areas in z-scores not only with that and with a table and with a calculator, but also on a spreadsheet. We'll go to the spreadsheet now. The same spreadsheet we looked at in lecture 5. This grading on a curve 1. We can also use a couple built-in commands to do a couple different things here that I want to show you today. And these are worth knowing, and you can check future work with these things. I think it's good. I might ask you some spreadsheet questions on tests as well, so it's good to know this, take notes. There's a built-in function called NORMDIST that if you start to type it in, gives you the syntax. It's got 3 main inputs. It's got the value of x that you're thinking about, the mean of the standard of the normal distribution you're thinking about using, and its standard deviation. And then this fourth one is cumulative. That's, I think, assigned to be true automatically as a default. Don't worry about that. Just leave it as is. How do you use this? Again, you plug in the value of x, in this case, say this exam score of 68. You plug in the mean of the normal distribution you're using, which was 70 for these exam scores, and the standard deviation. I think we don't have to bother putting the true. Actually, I didn't test that. What is this going to do? It's going to return the percentile, actually. It's going to return the area under that normal curve with a mean of 70 and a standard deviation of 10 to the left of 68, which will be a little less than 0.5, right? 70 is the mean, 68 is a little lower than that. So the area to the left of 68 should be a little less than 0.5. We should get 0.4 or something, I believe. Okay, it does want me to put something in the last spot, I guess. You could put comma true. You could actually put a 1. A 1 stands for true as well. Maybe it's best to just put a 1, that's quickest. There we go, a little less than 0.5. Under a normal curve with a mean of 70 and a standard deviation of 10, the area to the left of 68 is about 0.42. And that person would be at the 42nd percentile. By the way, I could also do it this way. I could use their z-score of -0.2. I'm still talking about the same person up here who got 68. And use the standard normal curve with a mean of 0 and a standard deviation of 1 to get the same answer. You can see it already, 0.4207. Same answer, same area to the left. So you can use a spreadsheet to find those areas. You can also use the spreadsheet in the reverse problem, where when you know an area, you can find the z, or the x. For example, if I'm after the x or the z-score that corresponds to the 85th percentile, so you know the area to the left is 0.85, the function to use is NORMINV instead of NORMDIST. And what's the syntax for that? There we go. The syntax for that is, again, to put the x value, although the x value in that case is not the original x value of 68, but instead the percentile value, in this case 85th percentile, 0.85, then the mean and the standard deviation of the curve that you're after. If we do it for the z-score, we need to put a mean of 0 and a standard deviation of 1. There you can see the answer is a little bit bigger than 1. The z-score of about 1.04 is going to correspond to the 85th percentile. 85% of the area is to the left of 1.03, or 1.04 if you round it. I can also do it for the actual scores. Again, it's NORMINV, stands for inverse normal. If I'm after the 85th percentile score, I type in a 0.85. The original mean was 70, the original standard deviation was 10. That's going to return an exam score at the 85th percentile. It's about 80. Okay? So NORMDIST finds areas when you know x or z. NORMINV finds x or z when you know the area. They work in reverse. They're kind of like inverse functions. Okay? If that went by too quick for you, you can watch the video. Right? And you can practice it yourself and try different examples. All right, what's next? We got a lot of things to do today. So I got to go pretty quick, and that is going to be the typical thing, is I do have to go pretty quick. I am trying in both your homework and in class to take the advice from this book, the Making It Stick book, to interleave lots of different topics, sort of over and over again. It makes it a little bit more of a struggle at the time, but if you continue working that way, you have to think harder, though you should come to class ready to think, and that does help improve your brain connections. It helps you learn things more deeply in the long run. So I'm trying to practice what I preach here. Okay, so we've been talking about correlation and regression. Again, I focused on this formula so far because that's the formula in the book. Again, it's not really a formula that many people use. Hardly anybody uses it, as far as I know. However, there is one benefit to it. It can promote a bit of understanding, and I've mentioned this already. It can help you see why the correlation is positive when you've got an upward trend and negative when you've got a downward linear trend. And I found a nice picture to illustrate this. We're looking at a scatter plot of married couples where the age of the wife is on the horizontal axis and the age of the husband, H stands for husband, is on the vertical axis. Each point represents a married couple. For example, that point, the age of the wife at the time of the survey looks like about 40, and the age of the husband was around 31 or something. Okay? There the wife was about 40 and the husband was about 31. On the flip side, here's an example where the wife was younger than the husband. The wife was about 33 or something, and the husband was about 45. Okay? And there's an upward trend, as you would expect. Wives that are above average in age tend to be married at any given moment in time to husbands that are above average in age, and vice versa. Again, in the formula, these quotients here, these fractions represent standardized values of x and y, essentially, because you're subtracting a mean and dividing by a standard deviation. So they are positive for points that are above average and negative for points that are below average. Points that are over here are above average for the wife, corresponding to these plus signs, and points that are over here that are below average for the wife. Points that are above the mean of the husbands, by the way, these lines are supposed to be at the means. This is the mean of the wives, this is the mean of the husbands. Points that are above the horizontal line are above average for the husbands, plus signs in the second spot. And points that are below average, below the line are below average for the husbands, 2 minus signs. Most of the points in the diagram, because of the upward trend, are on the upper right and lower left, corresponding to products where both factors are either positive or negative, giving you positive products. Very few of them are in the upper left and lower right, where the signs of these fractions are opposite, and therefore the product is negative. You get the idea? Because there's so many more points in the upper right and lower left, they contribute much more strongly to making the correlation positive than the few points in the upper left and lower right do. If, on the other hand, the points had been in the opposite direction with a downward negative trend, like this, then most of the points would be up here and down there, contributing to negative products, making the correlation more likely to be negative. Okay? That's the main benefit of this formula for us. It can promote that little bit of understanding. It's not enough to know that the correlation is definitely between -1 and 1. Okay? But it helps you see why it's positive in some cases and negative in other cases. I did mention last time that there are alternative formulas for the correlation and as well the slope of the regression line, and I'm about to show you those formulas. I'm not going to use these formulas today, but I probably will next time. Okay? They're kind of complicated looking. There's a bunch of them. And a lot of these formulas involve notation with 2 S's right next to each other. SS, like that. Whenever you see 2 S's next to each other like this in a stats book, it almost always, as far as I know, stands for sum of squares. This is shorthand for sum of squares. In this first formula that's here, there's also a subscript, 2 x's. This is SSXX, SS sub XX. Why the x's? Because of the x's over here. Why is it a sum of squares? Because you are adding squares. This is the definition of what SSXX is right there. And it turns out through some manipulations of summations, which I'm not going to get into, you can also write the formula this way. All right? You can do the same kind of thing for the y values when you've got bivariate data and create something called SSYY. It is again a sum of squares, but this time of y values. You're adding some squares. And once again, by analogy, you can do some summation manipulation to rewrite that formula this way. The next one I'm going to show you is also another SS. However, it's not really a sum of squares, even though we're still using the SS. I guess that belies that this is always a sum of squares. Not the right word to use in that situation. It's a sum for sure. These are not squares, though. These are different quantities. I guess it's analogous enough to these other formulas that we still use the SS notation. But it's not really a sum of squares. Once again, you can use some summation manipulations to rewrite it in another way. Once you've got these numbers, there is an alternative formula for the correlation right there, and an alternative formula for the slope right there. The formula for the intercept we saw last time, we wrote like this. You could write that with some summation notation as well, because the mean of the y's is the sum of the y's divided by n, and the mean of the x's is the sum of the x's divided by n. I didn't put it on the slide here, but that's another formula you can write down. And you can combine these fractions because you already have a common denominator. Once you've found the slope, at least, you can use this formula. There's actually a version of this formula that works without the slope in there too. But let's just leave it that way. Why am I bringing this up? One reason is because you may see this notation in the future. Actually, it does come up in our book later in the book, though not in the same way as this. It is in other books, including non-stats books, including economics books sometimes, advanced business marketing, probably financial analysis books. You might see these formulas, or you might at least see these SS symbols, okay? So that's one reason to introduce it to you. A second reason is historic. These are the formulas that people used before they had calculators and spreadsheets. These formulas right here were relatively easy to use to find these SF values. This formula was a bit more complicated because they still had to find square roots without calculators. That was a bit more complicated, but it was still doable if you knew the tricks. And this formula was relatively easy to use. You could, once you got these two numbers, essentially you can do some long division when you're doing it by hand to do that fraction. So it's historical. That's a second reason to bring it up. And a third reason to bring it up is we'll get more practice with spreadsheets. Okay? I don't want to get into details about this because of time today, but next time we'll do an example, and I might give you an electronic homework related to that. I'm going to skip over the facts about correlation. You should know these, like I mentioned for the quiz today and possibly next week, but I'm going to skip them today. I'll give you a few seconds to glance at them again to remind yourself of them. Maybe, okay, I'll go ahead and say something again right now. I just can't resist. No distinction with correlation between explanatory and response. There is a distinction, and it's important to keep the distinction for regression, however. You get the same value for R because the formula for R was symmetric that we looked at. Both variables have to be quantitative. R stays the same if we change measurement units or scale. R itself has no units. You should never see units on a correlation. That could be a true-false type question sometime. Positive R indicates positive association and a strength of a linear relationship. Negative R indicates a negative association and a strength of a negative linear relationship. It doesn't say anything about the strength of curve relationships. Usually if it's a strong curve relationship, R will be close to 0, in fact, though not necessarily exactly 0. And it's sensitive to outliers. Okay, all things you should know. I'm going over these very quick. Here were the formulas for the regression line that we used before. You should, for the quiz, today and possibly next week, be able to use these formulas. Not only to find the slope and the intercept, but also once you've got the regression equation, you should be able to use the regression equation itself. Just to make up an example here on the spot, what if the regression equation is y hat equals 5 plus 8x, and I asked you to find the predicted value of y when x was 3. All you have to do is plug in 3 into the equation. Y hat is the predicted value of y. Y hat would be 5 plus 8 times 3, which is 5 plus 24, which is 29. If I also told you a data value, a data point for this was, say, 3, 35, you should also be able to find the residual, the prediction error. I called that E last time. That's not the number E. It's the data value for y minus the predicted value for that same value of x. These 3's need to match here. That same value of x, what's the prediction error or residual? Do y minus y hat. The data value is 35. The predicted value is 29. The residual is 6 in this case. By the way, it's called E because E stands for error. We do think of this as a prediction error as well. Residual and prediction error are basically synonymous. All right, you should know that certainly residuals can be negative as well. It's positive when the data point is above the regression line, and it's negative when the data point is below the regression line. Y is the second coordinate of the data point. Y hat is the second coordinate along the regression line for that same value of x. Again, these 3's have to match. All right, come back to the screen here. Quickly going over properties about least squares regression lines. I haven't talked about why it's called least squares before. I think I'll do that next time. I will talk today about why it's called a regression line. Kind of a strange word to use. The distinction between explanatory and response is essential in regression. If you swap the roles of the variables, you get a different answer. And it's not the inverse function. They're not inverses of each other like I mentioned last time. The second fact basically says that in terms of standardized units, y changes by less than x along your regression line because r itself, the correlation, is between -1 and 1. And in fact, you can find, you can be more specific. If x increases by one of its standard deviations, y increases by r bits. Maybe I should verify that briefly here today. I suggested that you try to verify it last time. I wrote down this equation. There's your general equation of a line, and I said, whenever you have a line, to find the change in y, you take the slope times the change in x. Again, delta y means change in y, and delta x means change in x. We can apply that in the situation where this is a regression line. The slope is r times sy over sx. By the way, don't get confused about the different notation. M that you use in like a pre-calculus class is the same as B1 that we use in stats. B here that you use in a pre-calc class is the same as B0 in stats. Okay, it's just different letters. But the idea is the important thing. I can replace that slope with what it equals for regression lines. And if x changes by one of its standard deviations, if the change in x is s sub x, I can make that replacement. I can replace delta x with s sub x. And it simplifies because the s sub x's divide out. They cancel, so to speak, to become a 1. And what you're left with is r times sy. And that's telling you the change in y is r of its standard deviations. Oh, I forgot about my light. Is that done? Does that make the board easier to see? Okay. Try to keep that on. The least squares regression line always passes through the point whose coordinates are x bar and y bar. The mean of the x's and the mean of the y's, though that's almost never an actual data point. And r squared is the better measure of the strength of the relationship. And in a problem, whenever you see the phrase explained by, that's vague, but go ahead and square r to answer the question. Okay? And by the way, you typically write r squared as a percentage. So if r squared is 0.5, for example, you typically write it as 50%. 50% of the variation in the y values is explained by the regression line. Okay? It's a measure of strength. The closer that is to 100%, the closer it is to a really strong relation, whether it's a positive slope or a negative slope. Staying awake? I know I'm going fast. We've heard all this stuff before. I hope you're thinking as I go here. We talked about the point of a regression line to predict y when you're given x, or to predict or estimate the mean of all the y's when you're given x. And sometimes the slope and intercept have meaning as well. Let's go back, okay, we're going to go back to the baseball example in a minute. But I did briefly want to say why it's called a regression line. What in the world, why is it called a regression line? What does the word regression mean? It's historical. The person who coined the term was named Sir Francis Galton, who lived in the 1800s mostly. And he called it that because he was looking at data for father and son height at maturity, when they were full grown, of the relationships, and he saw a regression toward mediocrity in the sons. What did that mean? By the way, here's what Sir Francis Galton looked like. Okay, typical 1800s guy. What did he mean by that? He was, in particular, looking at fathers who were above average in height, and saw that their sons were above average in height as well, however, not typically by as much. Say that again. He was looking at the fathers who were above average in height, and saw how tall they were, and then he looked at their sons, and typically they were above average in height as well, but not by as much. They were a little shorter than their fathers. They had regressed toward mediocrity, in his words. And that's why he called it a regression line. He was looking at data like this. I'm not sure if this is his actual data or if this is just somebody else's data or made up data. He thought of the father's height as the explanatory variable and the son's height as the response variable. And in particular, for fathers who were 72 inches above, or 72 inches tall, he had a bunch of people that were really close to 72 inches tall. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Like about 20 people who were really close to 72 inches tall, 6 feet. What was the average of their sun's height? If you take all the points in this column here close to 72, the average for the sun's height is close to 71. They had regressed toward mediocrity. Why? Well, here's an intuitive explanation for that. The father's above average, okay? But that doesn't necessarily mean he marries a woman who's above average in height. He's got genes that make him be tall, and his son's got his genes that make him likely to be tall as well. However, possibly because his wife is shorter, or even average height, that the son, of course, gets genes from the mother as well, and intuitively that could cause the son to be lower in height than the father on average. Okay, that's one way to think of it. You actually can also not bother bringing genes in the picture necessarily. Well, okay, I guess this is what let's say still does bring genes into the picture to some degree. The father's above average in height, possibly because of genes to some extent, but possibly because of luck to some extent. Good nutrition, lived in a good area, that kind of thing. On the flip side, the son has the father's good genes for height, if you think of height as being good. Okay, I'm not making any judgments about that. And maybe the son is not so lucky. Maybe the nutrition's not as good, maybe the area they live in is not as good. Okay, you might say, well, if the father was raised well, then the son should be, but not necessarily. There's a little bit of a couple intuitive reasons why this phenomenon happens. Okay? And it actually happens a lot in a lot of situations where people sort of regress to mediocrity. For example, we'll also look at baseball player data of rookies of the year and see that typically their second year is worse than their first year. It's called the sophomore slump. It's basically the same reason. Maybe their first year they were good and somewhat lucky. In the second year, they're still good, but maybe they're not as lucky, is the idea. Let's go back to baseball. We looked at this data for Joe Mauer, in particular this one I'm going to look at here today. These are Joe Mauer's different seasons where he had at least 500 at-bats. I kept track of the number of home runs and the batting average for those seasons and plotted them. We saw there was an upward trend. In seasons where he had more home runs, he also tended to have a higher batting average. That doesn't always necessarily happen. At least in my mind, it wouldn't have to happen. In fact, I know from some experience in watching baseball and listening to people talk about baseball that sometimes when you're trying to hit for power, you don't do as well on your batting average, right? Your batting average might go down if you're trying to hit home runs. And so I was trying to think of, okay, is there a baseball player who sort of radically changed how many home runs they hit and did their batting average go down? And the first person who came to my mind as a possibility was David Ortiz. Yeah, he used to play for the Twins a long time ago. Maybe you don't know that. Back 2000, 2001 time frame. And back then, he didn't hit so many home runs. I hypothesized that David Ortiz might be one of these people. The Minnesota Twins, misusing his talents as really a pure home run hitter, tried to get him to hit more for average back in the early 2000s. At least that's my memory. I looked at the data. His average wasn't that great, actually. And he also didn't hit many home runs. It was like 10 a year for the Twins. But when he went to the Red Sox, he all of a sudden became a big power hitter. He was hitting like 30, 40, and there was one season where he hit over 50 home runs. And so then I thought, okay, did his batting average go down? Well, it was a weaker relationship than Joe Mauer's, but it was still a positive relationship. Here's David Ortiz's data. I forgot to add a label to this. This is for seasons when he had at least 300 at-bats. He had a lot of seasons within the 400 at-bat range, so I didn't want to use the 500 at-bat threshold, which maybe makes this analysis less valid. If you have fewer at-bats, you're going to get fewer home runs. But it is what it is. It was a little weaker correlation. R was like 0.2 something. R squared was pretty close to 0. 0.086, can you see that? 8.6%. So it definitely was a weaker linear relationship, a weaker positive linear relationship, but it was still slightly positive. I will continue looking for a baseball player who might have a negative relationship between home runs and batting average. This was just the first person who popped in my mind when I was thinking about it early this morning, in fact. Okay? So this is the nature of trying to think about stats and whether it tells you anything, is you have ideas and you go look stuff up where you gather data in some way. I was doing that this morning. I had a hypothesis, I wanted to test that hypothesis. I kind of contradicted myself a little bit in the last class. I called this an important note, but then I said, you don't really need to know it. And both of those are actually true, okay? It is important. It's important to know for statisticians that the two regression lines you can get by swapping the x and y are not inverse functions of each other. So it is an important note in that sense, but it's also true that you guys don't need to know it. Okay, but it's there. I won't test you on it. We talked about residuals last time, as well as on the board here today. I already erased it. Here's more detail on residuals. I did not show you this kind of slide last time. Getting close to quiz time here, hang on. A residual, also called a prediction error, is y minus y hat, a data value, a y-coordinate data value, minus the corresponding predicted value for the regression line for a given value of x. In the example on the board, x was 3. By the way, I remember the order of this by looking at this formula, observed y minus predicted y, and remembering that O comes before P. Okay? Observed value, or actual value if you prefer, minus predicted value from the regression line. O comes before P, so does A come before P. That's the way I remember the order. It can be positive or negative. It's important to make residual plots to test for whether it's a good idea to use regression. It's a little hard to see this example here, the scales. This thing's kind of in the way here. Gross credit card sales versus item count. Don't worry about the application there. Just note that if you make a residual plot for that data, points that are below the line correspond to points in the residual plot that are below 0. Points that are above the line correspond in the residual plots to points that are above 0. Okay? You're measuring with a sign, S-I-G-N, plus or minus, how much a point is above or below the regression line. For example, point 21 is above the regression line by how much? That distance right there, that's a positive residual, corresponds to this distance right there. If a point's below the regression line like this one, think of that as the residual with a negative sign because it's below, its residual plot is below 0.